So let's look at how you would go about constructing a reactivity series. First of all, when you're trying to construct a reactivity series, you always want to make sure that your oxidized species, that is, the species without the electrons, are on the left-hand side. And then it's in equilibrium with the reduced species, so the species with electrons. However, the only way that you can go from being an oxidized species to being a reduced species is by picking up electrons, perhaps one, perhaps more than one of them. And when we have a whole series laid out, then what we can do is to arrange them such that the strongest oxidizing species, the ones that would most like to get the electrons, are in the lower left quadrant. So for example, commonly what you would see as the strongest of these oxidized species may have been F2, being highly electronegative. It likes to grab any electrons available to it so that it becomes a reduced species. Of the reduced species, the one that is substances that like to give out an electron, here we put the strongest one on the upper right corner. These have to follow, because if you have a strong electron receiver, the reduced species must be a weak electron giver. An example of a species that like to donate electrons strongly might have been potassium metal. If we set it up as such, then the trend you would see is that if you have a strong electron donor, and a strong electron acceptor, then you would find them with a positive slope. When this happens, it suggests to you that this pair of reagent will be able to react. On the other hand, if you find that it's a weak electron receiver, but a strong and also a weak electron donor, this pair of reactant would not have any reaction going on. Once we're aware of this general rule of thumb, what we can do then, in order to solve the question we encounter in the lab, may simply be first to write out all the species in the same format, so that the oxidized versions on the left-hand side, the version that have received electron is on the right-hand side. Repeating it for all 5 of the reactions under investigation, we may encounter a series as such. So what's left next is for us to arrange these in the correct sequence. If you look at the first reaction, we're looking at reacting iron 3+ with iodide ions. So we can remove the other 3 because they're not in contention right now. Between these two species, iron 3+ and iodide, we see that they do react. So we know that we've currently placed them in the correct sequence, so that we will have iodide on top and iron on the lower stack, such that if we're going to connect them, we would have a positive slope diagonal. We can repeat this with our second reaction, where we see that sodium hypochlorite reacts with iron 2, so that this species reacts with that species. So we again have this relationship. If we were to place this stack above iron, then what we expect is that this and that will not be able to react, which is not what we see. At this point, we have the sequence of these 3 figured out, So then what we can do is to look at the reaction between ClO- with bromide ions. This is a reaction where we see that they have no reaction with one another. What this suggests is if we place it on top, the bromide reaction on top of the ClO- equilibrium, then we would have got it the wrong way around. So what we do is we slide the stack along such that it accurately indicates that there's no reaction between ClO- and Br-, the bromide ions. Finally, at the end, we looked at the reaction between chloride ions, between bromide ions and chlorine water. Here we see that they do react, so what we need is chlorine to be lower in the stack. Shoveling things a little higher up, we have a reactivity sequence as such. So to recap what we have seen in all of our reactions, in our first reaction, we saw that we could take iron, react with iodide, with iron 3+, reacting with I-. That is an allowed reaction, and this is represented in our scheme. In the second reaction with ClO-, we have iron 2+, and there's a reaction between the two. So then this is also accurately represented in our diagram. And then we see that between ClO- and Br-, there's no reaction, and this is also accurately represented. Finally, our last equation, where we have chlorine water reacting with bromide ion, a reaction exists, and this is also accurately shown here. At this point, we've finished constructing a reactivity series that is congruent with our observations.